Hello everyone, and welcome to this new colloquium from the Severo Ochoa program of the Instituto de Astrofísica de Andalucía. Today is our pleasure to have with us Rin Fares, so thanks for accepting the invitation to come here and give this colloquium. So Rin is currently an associate professor at the United Arab Emirates University, where she is also the coordinator of the Master of Space Science. And she's specialized in the study of stellar magnetism and star-planet interaction. So her talk today will be about this topic, star-planet interactions. Rin did her PhD at the University of Toulouse in France, and then she joined to the University of St. Andrews and later to the Catania Observatory as a postdoc. And before moving to Lebanon as a teaching faculty. And now she moved to the United Arab Emirates 6 years ago. She's, as I said, the coordinator of the Master of Space Science. So she will be talking about star-planet interaction. So the floor is yours.
Thank you so much. Okay. Yes. Thank you so much, and thank you for okay. Thank you for the invitation and for being here. I know it's a challenging after yesterday at the Fecha, so thank you for being here. So today I will speak to you about star-planet interactions, but also a lot about magnetism, and I hope that I will convince you why understanding stellar magnetism is absolutely important if you want to interpret anything related to star-planet interactions. Okay. Do I have to? Okay.
Click once.
Okay. So when I'm talking about star-planet interactions, obviously I'm not a planetary person, so I'm talking about exoplanets. And just to start, I want to tell you where exoplanets are, not in our galaxy, but where are they relative to their stars. So what you have here on the y-axis, you have the planet mass or the minimum mass of the planet. And on the x-axis, I didn't plot the distance of the planet to the star, but I plotted the ratio of the distance of the planet divided by the radius of the planet for known stars. So you see, we do have a lot of exoplanets a little bit everywhere. But just so we put it in context, if we plot Earth and Mercury in our own solar system, this is where they would be. Earth is at about 215 solar radii, and Mercury is a little bit less. And if some of you are interested in studying the sun, and like me, you were interested to know if Parker's solar probe will survive its closest approach to the sun, this is where Parker's solar probe was approximately in its closest approach to the sun. And you see that a lot of these exoplanets are 2, 5, or even 10 times closer than Parker's solar probe in its closest approach to their stars. So they are really fully embedded in the magnetic field and wind of their stars. Many of them are massive. We call them hot Jupiters or hot Neptune in some cases. And this is, of course, a bias of our detection techniques. We are aware of that, but they are there and they are surviving, and they are amazing laboratories for us to study star-planet interactions. So again, to do the parallel with the solar system, last year, this is a picture from Spain. But last year we had a solar storm in May 2024, and a few days later, we had these amazing aurora that were visible, I guess, all across Europe, even to Sicily, but they were visible also in Spain. Again, this is at 215 solar radii, but those exoplanets are at sometimes 8 or 10 stellar radii from their stars. So what kind of star-planet interactions we have? They are extremely irradiated, and they do have sometimes an evaporating atmosphere, and we can do a lot of studies about that. And I guess some of you here in the audience work on this. So they are irradiated planets. But in addition to that, since they are embedded in the magnetic field of their stars, you can expect a lot of magnetic, or what I'm going to call stellar wind interactions. So these are interactions between the magnetic field of the star and the planet. Regardless if the planet is actually magnetized or not, you could have these kind of interactions. But of course, when we think about massive planets very close to the stars, you also have tidal interactions that could happen. And those tidal interactions will generate tidal bulges, not only they will affect the planet, but also they will generate tidal bulges on the stars. Now, these star-planet interactions will affect the planet and the star. I'm going to start telling you just some ideas of how they affect the planet, and then I will pass to the star. So for the planet, of course, they affect the planetary atmosphere, a lot of chemical reactions in the planetary atmosphere, evaporation of the planetary atmosphere, and so on. You could see some aurora or radio emission due to auroral emission from the atmosphere of the exoplanet. And yeah, sorry, I didn't mention, but these are color-coded like these ones, but it doesn't matter. These are star-planet interactions overall. The tidal interactions will affect, could affect the planet through tidal heating. That might be one of the reasons of some planets being big. Actually, they are bigger than what we expect them to be, but it does not explain fully their size. But anyway, it's there. And of course, it will affect their orbital evolution as well. And this is amazing. But the challenge with the planets is that somehow it's very hard to observe them. And even some of these known, I would say, SPI, it's quite challenging to observe them. But we can see the stars, and we can observe the stars, and we can develop a lot of observational campaign on the stars. So one idea would be to check how these star-planet interactions could affect the stars as well. It was suggested that they might affect actually the rotation of the stars, so the stars don't slow down. They can still be rotating relatively fast with time. And so this will generate, or this will affect the activity, maybe additional flaring or additional activity on the surface of the star. They could affect the stellar inclination through what we call tidal instabilities. And of course, they might affect the generation of the magnetic field of the star. So the point is, if we are thinking about these star-planet interaction, whether from the planetary point of view or the stellar point of view, the magnetic field and activity is a main thing. So you would want really to study it. So how do you study that? There are different ways to do it, really very, very different ways. You could pick a system and study it in a specific way. For example, flaring of the system, activity of the star, and so on. Or you could design a sample, for example, do a sample or a survey of planet hosting stars. We have done that previously. I observed 10 planet hosting stars, but also like PhD students and postdocs working later with me observed more, but this was done during my PhD and in my first postdocs. Or you can do a multi-wavelength observation for planet hosting stars, particular objects, because it's harder to get it. And that would be to probe the whole system from the photosphere of the star all the way to the planet, whether it is in radio, UV emission, X-ray, and so on. Okay, and during this talk, I might be telling you a little bit of some of these programs that we have done in the past. But as I told you, a main thing is to understand the stellar magnetism. And since I am here, and I guess a lot of you do work on stellar activity, but activity as activity indices, I would say, I think there is not many people working on large-scale magnetic field of stars. So I would like to take some time to explain to you the methods we use. To study stellar magnetism, the idea is quite simple, I would say. In principle, if you have spectral lines that are forming and you have a magnetic field, this is what I'm going to call the direct problem. You have Zeeman effects. We know it from the sun. So this is the sun, actually a sunspot. You have the spectrograph, we slit here. You see spectral lines, and you do have Zeeman splitting in the spectral lines or broadening, okay, due to the magnetic field. Now, there is something that is very interesting, which is not only you would have a splitting in the spectral line, but the new spectral lines that form are polarized. And this polarization will depend on the orientation of the field. I'm going to tell you in a bit. I'm going to show you an animation to understand it better. And it will depend on the rotational phase of the star. Now, there is nothing we can do, not even for the sun, to just simply do a camera, for example, that will look at the sun and give us the magnetic map. So you have to do an inverse problem, I would say. So what we do is we can observe the polarization to deduce the magnetic field. But let me just tell you before how the field orientation and the topology of the field affects the polarization. This is an animation here of a star. And let's imagine the star has no magnetic field, and there is only one spot that has a magnetic field. If you don't see the spot, this is the polarization signature that you have here, okay? If you don't see the spot, there is no polarization in your line. If you see the spot, this is a radial field. So the field is always pointing towards you. So when you start seeing the spot, you start seeing actually a polarization signature. And if you notice here, the polarization signature has always the same shape. It will vary in amplitude, but it has the same shape. That's simply because the field is always pointing toward you. If you have an azimuthal field, which is like a donut, or like, you know, along the azimuth, if you look at the polarization signature, you will notice when you start observing the field, it has a shape and it will flip. That's because the field is pointing toward you, then pointing in the opposite direction. So what we can do is we can collect a time series of polarized spectra, and we put them in a code that is a tomographic imaging code, pretty much like what is used in medicine. So we put these polarized spectra in this code, and we reconstruct the large scale magnetic field of the star. Again, we're not reconstructing spots. We cannot see the spots. We're not reconstructing them here in this technique. This technique has its limitations. So small scale field, they can cancel out and you don't have their signature in the polarization spectra. But what you can do at the end, this is an example of the reconstruction. You reconstruct the largest scale magnetic field. So dipolar, optipolar, multipolar, but larger scale. This is an example here in the radial field component, the azimuthal field component, and the meridional field component. And you go from actually the time series of polarized spectra, you know the magnetic field of the star without really being able to map it or image it directly. Now, to collect these polarization spectra, I'll just mention it because if some of you are interested, you should use not only a spectrograph, you should use a spectropolarimeter, which is interesting because it gives you the spectra, the unpolarized spectra, and then the polarization as well. There is several of them. There is Espadon at CFHT in Hawaii, Narval previously, now Neo-Narval at TBL, Telescope Bernard-Lion in France. These are accessible for the European community, even if they are not in France, for example. There is Hartspol in La Silla, also that does polarization. These three instruments actually are in the optical wavelength, and right now there is SPIs at CFHT that is in the infrared. One thing that I want to mention really briefly before going on is that the polarization signature is very weak. So usually it's within the noise. So we do use multi-line techniques similar to what is used to detect exoplanets. So you take the information from many, many lines in the spectra, 4,000, for example, for some F stars. You take the information of all these lines, and then actually what you can reconstruct is this polarization signature that you see here. Taking 4,000. So it's really very small. If you look into individual lines, you see nothing. You have to extract the information from many lines there. All right. So I'm going to give you just some examples of some stars that we observed. One of these stars is HD 189733. For the exoplanets community, it's a very known star because it's an active K-dwarf. It has a planet around it that transit, goes in front of the stellar disk. And I'm showing you here just some examples of the polarized spectra. So you see the observed one in red and the reconstructed one by the code, by Zeeman Doppler imaging code in blue. Those numbers that you have here are the rotation of the star. So it starts randomly, let's assume at 0.4, and it ends at 2.4 or 5, 3, and 5. So you have to observe the star through at least one rotation and a half, or 2 rotations. That's to be sure that the parts that you are seeing are coming back to be able to reconstruct that. From this, this star has a hot Jupiter around it, orbiting at 2 days. We will come back to the star because hints of star-planet interactions were detected for it. So this is the kind of magnetic maps you have. This view is what we call a polar view. So it's as if you are looking at the star from above. So this center of all the circles here is actually the pole of the star. and each of these circles are different latitude. The very thick circle is the equator of the star. And when you reconstruct the magnetic field, you reconstruct the radial, azimuthal, and meridional. You know where the regions, the magnetic regions are. You can calculate the strength of the field. For this star, it's about 42 for this particular epoch. And I mean, if you just look at this, you see that most of the field is in this component, azimuthal. So it's more of actually a toroidal, what we call toroidal field, forming a kind of a torus around the star. And when we look, for example, at the radial field, it's not a simple field. For our star, we have mainly a dipole that becomes a little bit octupolar during the solar cycle, but mainly it's a dipole. I mean, here clearly you see you have many regions, so it's a multipolar magnetic field. But this is just an example. You might be interested, and I'm sure you are interested, especially in JG436, which is a planet hosting star, but this is an M dwarf. So this star was observed in May 2015. And when we reconstructed the magnetic field of the star, this is what we see. So I would say most of the field is in the radial component here. It's dipolar, pretty much dipolar. So a tilted dipole. And the average magnetic field is 16 Gauss, so less than the other one, but this is to be expected for these stars. So you can compare a lot of stars, but the idea, because again, I mean, my goal personally was to also understand if star-planet interactions, when they affect the star, will they change the generation of the magnetic field of the star? So to do so, you can compare actually the magnetic properties of stars with and without hot Jupiters. And we do that, so we have samples of cool stars that are hosting planets versus a sample of non-hosting planets or non-hot Jupiter as well. I mean, they could be hosting planets that are not discovered, of course, yet. And you can compare the topology of the field, the strength, if it is axisymmetric, if it is multipolar or not, and so on. And I'm listing some of the papers actually from where I got all the data to that. So how do we do that? We do that, if some of you were familiar with this, we call this a confusogram in the community, because we have to present 5 different things on one plot, but I'm gonna hopefully like go slowly on it. So there's nothing yet. So the way to describe the field properties, we're gonna draw it, or we're gonna plot it on this plot, which represents on the y-axis the mass of the star, and on the x-axis you have the rotation period of the star, how fast the star is rotating. Okay? Before adding the stars, I'll just tell you that each star will have a symbol. The size of the symbol will indicate how strong the field is. Okay? The biggest the symbol, the strongest the field. The color will indicate if it's more radial or poloidal or azimuthal. So red is radial and blue is azimuthal. And the shape will tell you if it's axisymmetric or not. Now let's put the stars there. We put the stars there and you see a zoo of possibilities. So I guess it's really hard to say which star, what are the properties. However, for people who do dynamo generation in stars, there is a property, I would say, or like a number that is very important, which is the Rossby number. The Rossby number will measure, or it's a number that will measure, I would say, the rotation period of the star, and it will divide it by the convective turnover time. These stars that are solar-like stars, I'm not talking, I mean, I'm going really here to about 0.7 solar masses, so I'm not showing you here the M dwarfs. But these stars, the upper layer of the star is a convective layer, okay? So you check actually the rotation of the star, you divide it by how much time the convective cells are taking time to do the convection. And if you plot this line here, this line corresponds to Rossby number equal to 1. Now we start seeing some things. So you see that the stars that are here are like, I mean, we don't care about what they represent, apart from, let's consider the size, the color, and the shape. Okay, whether it's poloidal or not, it's okay. So they are reddish, roundish, and small, and the stars that are here are more star-shaped, bluish, and bigger. So If you add if you add planet hosting stars, their names here are in red, are in green, no differences. We didn't see any difference so far. So it seems that although star-planet interactions are happening, they don't seem to affect the general properties of the magnetic field of their stars. So we might think, okay, that's fine. You have done some work on this, but why do we care then about magnetic field? And I hope that, I hope in the rest of the talk, I will convince you that it's important. But before doing that, because maybe some people in the audience have done surveys with, hundreds of stars. So you might be wondering why we don't have hundreds there. And I really would like just briefly to mention that the Zeeman Doppler imaging is very, very time consuming on the telescope. So we had a proposal with a colleague, Antoine Strugarec in France. We wanted to reconstruct the magnetic field of the star, but also to study the activity of the star doing purely spectroscopy. And we observed with Néo Narval and Sophie in France. So on Néo Narval, to do the minimum to be able to reconstruct a map, we needed 18 hours of observation for one target. And doing only spectroscopy, we needed 2 hours, and that was to observe really intensely. So this gives you an idea why we cannot, do forever observations, I would say, of hundreds of stars in spectropolarimetry, because they need a lot of telescope time. So if star-planet interactions don't affect the larger scale magnetic field of the star, is it important to do any studies related to star-planet interactions? Well, I would argue that it's absolutely needed, and I hope I will convince you why. Because if you want to study star-planet interactions, not directly through the larger scale magnetic field, for example, you are interested in radio emission by the planet, you are interested by the interaction of the wind of the star with the atmosphere of the planet, and so on, you need to model the stellar corona. You need to know the properties of the wind. You need to know what is deposited on the atmosphere of the planet, and so on. So how can we do that? If you know, and if you calculated the magnetic field of the star, then you use this as a boundary condition, and you can extrapolate the field lines in the atmosphere. You can do it through different ways. People, colleagues and collaborators, they do wind modeling. So they take our maps, they put it in their code, and they let the wind evolve using MHD. Or you can take some simpler models, I would say, like a potential field source surface model. So this computation-wise is really not, you can get the results pretty quickly. But no matter which models you are using, if you have the magnetic map, you would get a more realistic representation of the corona of the star, and surely the stellar wind properties as well. So this is an example done with my collaborator, Aline Bidotto, from the Observatory of Leiden, where she took the map of this star was Tau Bootis, also a planet hosting stars. When you take the map, you can, import it in your wind modeling code, and then you can study the corona, I would say, of the star. What you have here, this is the star with the real map, and these are the field lines, along the corona. But you can also study what happens at the orbit of the planet. So what we're showing here, this is the orbit of the planet, and this is the star here in white, just like it. And she is representing here the speed of the wind. So you clearly see already that although these planets are very close to the star, actually, because the field is not purely dipolar axisymmetric, the planet would go through different configuration of the field and different properties, different densities kind of, or even different speed of the wind. And this would generate either an interaction to be possible or not, but I will not go into extreme details here. Okay, we have done that for many of the stars. This is again HD 189733 that I showed you before. This was a program called the MOODS program. So multi-wavelength observation of an evaporating exoplanet and its a star. And we observed the star for many epochs for this particular program. So 5 epochs of observation for the star, okay? This was in June 2013, August and September 2013, and then 1 year later and 1 year later. And we reconstructed the magnetic map, and then we reconstructed the field lines in the atmosphere. But let me just explain those field lines because it's like maybe weird. So all the white ones are the closed loops. So we don't think they will connect with the planet unless if the planet is inside of them. And all the blue ones are the open field lines. But what I want from this slide is just to tell you that already this star, this is not a star for which we know that there is a cycle. But already if you observe it between June, August, and September, you have a different corona for the star. So if you have any observation, of SPI, well, you need to know the magnetic field to understand what is the magnetic field that is causing actually these interactions to happen. What we do from this is also calculate, and I'm plotting it here, I'm calculating here the magnetic field of the star at the position of the planet. Okay, so to see what energy basically is deposited at the orbit of the planet. So what we found is that, okay, these are the different epochs of observation, the one I showed you before, but also previous epochs from my PhD degree, so my PhD time. So what we found, this is the magnetic field of the star, and this is the orbit of the planet. And you find two important things. One, the magnetic field of the star is very variable on the orbit. And two, it's not the same from one orbit to the other. And this was relatively, I would say, specifically when we study radio emissions, it was new because we would model the star with a simple dipole, and you would assume there is a perfect symmetry on the orbit of the planet, which we proved it's not the case. So even if you have a radio detection, you really have to understand well how it is produced. And this is the next one. So, well, the next idea there. So if you have a radio emission, of course, there are different ways to have radio emission of the exoplanet, but I'm just gonna briefly summarize here. You might be interested to know, and this is very interesting to do radio emission, because if you detect radio emission, you can actually infer the magnetic field of the planet. So the radio emission will depend on the magnetic field of the star and the magnetic field of the planet, and two other things, of course. If you know the magnetic field of the star and you have a radio emission, you would be left with one unknown, magnetic field of the planet, which we have no way to measure apart from radio and activity indices as well, that I'm going to speak about later. So for this same star, we modeled what kind of radio emission with Robert Cavana in 2019. And you see this is the radio flux as a function of the orbital phase. Again, you see for the three colors are three different observations. You see that it's very variable on the orbit. So any observation of SPI needs to be really very well understood to be able to say, anything about, I would say, the magnetic field of the planet. And you see here, this is an average over the orbit. Depending on the magnetic field of the star, you have amazingly a huge, well, for me, at least, it's a huge difference in what radio flux you would expect. So I'm going to speak, hopefully, I will finish on time, hopefully. I'm going to speak briefly about activity indices as well, because I know that Pedro and the group are also in that. So for activity indices, let's move to something now a bit different. Let's assume you have a spot on the surface of the star. The star is rotating. Well, this is how we measure the rotation of stars. The star is rotating. You will see the spot coming back after every rotation. And so you can detect the rotation of the star. Of course, this is very simplistic because the stars have differential rotations. They have spots that could be at different latitude and so on. But this is used, and this is how we detect rotation of stars. Now, where does SPI comes? It comes in the fact that if you have an SPI happening, it was really suggested in the years 2000 by Kuntz et al. That if you have tidal interactions, you would have two tidal bulges. The planet is orbiting between the observer and the star, and the observer will see one tidal bulge, then the next one when the planet is here. And in these tidal bulges, you have wave propagation, so you might induce some activity that is not really internal, I would say, to the star. It is caused by star-planet interaction. So it was suggested that you would have an enhancement of the activity that is modulated by the orbit of the planet divided by 2. It was also suggested that if you have magnetic star-planet interaction, so you have the planet connecting to the magnetic field of the stars, when you as an observer, you will see it once in the orbit, the planet moves and it comes back, then you see it again. So the modulation will not be by the rotation of the star, it will be by the orbit of the planet. In this paper of 2009, we showed that actually it might be much more complicated than that when you know the magnetic field of the stars. What I'm showing you here, I'm sorry if it doesn't show really well with the background, but this is the star, the map reconstructed with Zeeman Doppler imaging. Blue lines again are the open lines, white lines are the closed field lines, and this red line is the line connecting the position of the planet to the star. Okay? And you see that when the planet is orbiting, actually when the planet comes back between you and the star in the background is fully different. You don't have the same star. So it does not mean that even if you have a connection through magnetic interactions, well, when the planet is coming back, maybe this connection is not happening. And we suggested back in the time that it will be modulated by the beat period of the system, which is the period after which the whole system will be back to the same configuration. So was this found in the literature? Yes. In some cases, these star-planet interactions were found, but I will just speak to you about recent one, again of HD 189733, for which I have shown you all the magnetic Zeeman Doppler imaging map. So Wilson Colley we collected all the data actually, but he worked really on the spectroscopy that I did not work on in this particular paper. And he measured the activity indices, I would say, a specific way of measuring activity indices to see if there is an enhancement due to the planet or related to the orbit of the planet. And what they found is that for this particular epoch, only in August 2013, there is an activity enhancement related to the planet. This is the plot from Wilson's paper. So this is the orbital phase, and what you have here is actually the, I would say, the activity index, kind of a measuring of the activity index of the planet, and they see that there is a modulation by the orbit of the planet. Okay, but it corresponds to this. What does this tell us? I was just thinking like, okay, what does this tell us? Well, first, it surely tells you, this is a plot you have seen already. It surely tells you that August actually corresponds to this curve for which the magnetic field is maximum. So yes, star-planet interactions could be intermittent and like on-off, I would say. Sometimes they can happen, sometimes not, because it will depend on the magnetic field of the star and if the planet is able to connect with this field or not. It's not always the case. This is a possibility. The second possibility, in this paper of 2017, what I had plotted is, okay, so here you have the extrapolation of the magnetic field for the different epochs. I removed one epoch here, not for it to be overwhelming. But if you look here, this is the magnetic field of the star, just a different view. And those dots here are the footprint, the base of the line connecting the planet to the star. Okay? For different epochs. I mean, I had it in the paper. When Wilson analyzed the data and he found actually a SPI in August 2013, I went back to the paper and I realized that the footprints, they are all at one latitude, in this case, the equator, but one latitude. This is a star that is differentially rotating. The equator rotates at about 11.5 or so, and the pole rotates at about 16.5 days. So a big question now in the SPI community, if you have this kind of interactions and you have these footprints that will enhance the activity at different latitudes, it might be, this is something that we need to explore, it might be more challenging to detect them because you would have this one here that is moving, let's say, at 15 days, but sometimes happening, sometimes not. This one is moving at 11 days and so on. This is a possibility, but we are still trying to explore it. The other thing that was done with my collaborator, Antoine Strugarek, in 2022, he also has a wind modeling, and he took actually the map of HD 189 for August 2013, only one epoch, and he calculated the field line. What you have here is the Alphen surface, but I will not bore you with the details. what I want you to see is that you do have these connections, even actually when you take a wind model. So more complicated, I would say, or more complete than a simple potential field source surface model. All of them also connect to the equator. But something that is extremely interesting in Antoine's paper was the fact that we tried to see, okay, we have an SPI detection. Let's try to see what is the probability to detect this if our data were not sampled like that, if they were sampled in a different way. And he found that about 17 to 23% of times you would detect the orbital period. So almost 1/6, which is exactly what Colley finds in his paper. 1/6 epochs are detected, only that. So we also tried with one of my students to see if maybe this star is going through a really low activity phase, maybe then we can detect SPI. And what I'm showing you here is the activity index, the Mount Wilson, so also to measure the activity of the star as a function of time. This is the epoch for which we have a detection. So all what you need to see is that it's not at a Maunder minimum, for example, stages, just like as active as usual. So this is it. I will just hope to give you some takeaway messages. I think star-planet interactions are extremely important because they are a way, and this maybe I didn't mention, I should have mentioned it. If you detect star-planet interaction, even in activity indices, you could eventually calculate the magnetic field of the planet that we cannot measure otherwise. So either in radio or activity indices, and this is amazing. So they are amazing probe of the system actually, and of the properties, some properties of the planets that you cannot get otherwise. But my advice would be that if you want to do star-planet interaction, you really need to plan your observations extremely well if you are observing for particular epochs. And you need to know the magnetic field of the star. You need to know that to explain any radio or any kind of SPI that you detect. You need that to model it, because if you want to model these interactions and to understand which actually, which radio emission is happening, what type of mechanism is producing these radio emissions, well, you need to know the magnetic field of the star. And of course, if like me as well, you are just interested in stellar magnetism, you would really need to know the magnetic field of stars to understand dynamo processes in stars. And on this note, I want to thank you all and thank you for the invitation again. And if you have any questions, I'm happy to take them.
Thank you, Lynn, for the very nice talk.
Thank
so
you.
Now it's time for questions, both for people here and also for those connected online. So who wants to be the first? No one wants to be the first.
Yeah, well, I do.
Okay.
Just waiting a little bit, so okay. Because I think I have too many.
Let's start with one and then.
Okay, thanks a lot for this very nice talk, very understandable, with lots of hints on how to proceed with the work we all are doing.
This was, to be honest, my goal, because I wanted to start, the discussion and maybe even explore even future collaborations. This would be great.
Yeah, exactly. So yeah, regarding this last takeaway messages, what you said about observations, since we especially here we do observations. What would you be, or let me just rephrase that. How would you prepare an observational strategy for trying to detect and understand star-planet interaction, magnetic star-planet interaction? How would be your best strategy for that?
This might take the whole afternoon to answer. There are many, to be honest, there are many ways. So for example, in this work we are doing now with Antoine, we want really to explore activity indices. If you want to explore activity indices, I would say the best is to really observe the star, the planet also, the orbit of the planet extremely well. This is complicated because it means you will need probably to use observatories all over the globe. And not all of them, for example, they would you would be able to get the activity, the same activity index. For example, you can cover calcium, or in the infrared, you cover other, as you know, you cover other, spectral lines. But I would say, in my opinion, we should know the magnetic field of the star in parallel. And for activity indices, you would really observe intensely. But what I understand also from previous discussions is that this is a possibility. The other possibility is that maybe we just need really a huge database of data and then just do the analysis on these data. For some of these stars, you would always find the rotation. Like HD 189, you always have to clean the rotation. So maybe the other possibility is to try to clean the rotation of the star, clean if there is a long cycle, because some of the stars are cyclic, and then you would see it there. So in my opinion, if you want to do an observational campaign, you just observe the star really, really a lot. And it would not only be possible, I would say, in one observatory, because you are missing, these planets are on a 2-3 day orbit. So if you only observe at night, you missed already a big chunk of the orbit. So maybe if you observe in different observatories, and in my opinion, and I didn't mention it here, but there is a lot to do in the archival data. This is my opinion. Maybe the archival data for sure are not like these kind of observations, but I would still think personally that maybe in the archival data we would find things that answer some of our questions that we don't know.
We also would like to know the topology of the magnetic field. So we would like to do spectropolarimetry.
Exactly.
To get the map.
Yes.
And also, if possible, to do radio observations to try to detect this also.
Yeah.
Radio.
Yes.
So if we want to do everything at the same time now, it's very complicated.
It's doable. It's doable, but it's very complicated. Yeah.
But we can do it. So
yeah.
we have to come up with a strategy on how to do these observations that are taking all these aspects of the physics.
I agree with you. For now, to be honest, I mean, I just spoke about moves, but we have other campaigns where we actually did radio. We did radio. Well, spectropolarimetry in a way. If you do spectropolarimetry, you get the spectrum, but you can never observe really intensely because I mean, rather than having an exposure time of 10 minutes, you need 40 or 1 hour. So you cannot use a polarimeter in the polarimeter mode. So you have to do in parallel, I would say, spectroscopy alone as well. I mean, in some of the cases we applied and we got even HSC and XMM data all in parallel, so it's perfect, but it can be challenging. But I would say if the community, as a community, come together and we start maybe like doing, large surveys on some telescopes, well, we have more chances. If more community are interested, probably we will have more chances to get data, hopefully.
There are already a couple of online questions. First one by Etienne Bonacier. Etienne, can you open your mic? Yeah.
Yes. Hello, can you hear me?
Yes.
Fantastic. Thank you for the very, very interesting presentation. It was really stimulating. I am curious what is the monitoring frequency that you would think would be necessary in the radio band to capture these observations? If I understand, it would be on the order of days, but would hours be interesting? Would you be capturing months, years?
This is a challenging question since I am not myself a radio person, but I would say, well, the magnetic field of the star changes really. It depends which star. I mean, some M dwarfs are very stable and you have a very nice dipole for years, or maybe, well, this is our understanding. Some M dwarfs change really fast. I mean, I didn't show this confusogram all the way to the M dwarfs because it will be super confusing, So I think it will also depend on the star. For example, we have a star Tau Bootes. Well, Tau Bootes has a magnetic cycle of 8 months. The solar cycle is 22 years. So if you observe Tau Bootes like once a year, you would need then to think of the cycle and you would need to think at which phase of the cycle you are and what do you expect. I personally think you really should do a lot of observations, but then again, I think this is the problem of observers. How do you, how do you get telescope time? This is the other problem. But I would say it will really depend on the star. If the star is, again, very stable, maybe you can, stable with, I mean, some M dwarfs are really dipolar. So, I mean, even on the orbit, you wouldn't expect a lot of changes, I would guess. But these multipolar stars that very, very fast, you really have to do a lot and then, hope to find something.
So you would expect to find things on scales of hours also? Or are we talking seconds?
Oh, well.
Well, maybe we can discuss offline, but
Of course. I think in the radio community, they have these bursty radio, at least that were, well, for Taubutis, it was not a, it was, it's a possible star-planet interaction. So you have a burst, and then you can expect something maybe that is making the star overall being, like the whole activity level being higher. So you would see something in the background, but I'm not fully sure, actually. The background thing, I'm not fully sure. So yeah, I have to recheck actually for the radio detections, but I would say like a bursty radio detections, but I cannot tell you if it's seconds or hours, sorry.
no, thank you very much again.
There is another online question by Oscar Bermel. Oscar, can you open your mic?
Hi, do you hear me?
Yes.
Okay. First of all, thank you for the presentation. It was really interesting. For context, I'm doing my master thesis in studying the influence of the US planets on the rotational period. So, but we only take into account the tidal effects via the Roche limit and so on. So do you think the magnetic interaction could be taken into account to influence on the stellar rotational period?
Yes, I mean, yes, not for the answer. Yes, it's an interesting question. You could eventually, think and model, and this is what we do, what kind of mass loss you have from the star. And I'm not sure if it was done actually, but like maybe these interactions could, like if you only study the mass loss rate in the wind through these interactions. Yeah, I have to double check. I'm sure some of the work were done on this, but I do not recall the results on that. But you can eventually check and compare the mass loss rate through the wind and how it would affect, eventually the J dot, so the rotation. But I don't think, I'm not sure.
Okay, thank you.
Thank you for this very clear presentation.
Thank you.
I have perhaps a naive question, it's not my field. Which are the various candidates to detect star-planet interaction? Are the stars with high values of magnetic field or lower or low values? It seems to me that high values of magnetic field can trigger the interaction, or perhaps these values, high values, can hide the signal. Would you comment?
Yeah, this is not at all a naive question. No question in science is a naive question. Actually, this is very interesting. Originally, when we designed these samples to study, I mean, there was the study by Conferenciante who put some values, let's say, on the tidal interaction and the magnetic interaction and the possibility. So in our sample, we have some active stars and some inactive stars. And we find SPI, or like people, actually colleagues find SPI in the two cases. It's better for sure that the planet should be, I mean, if you model the wind, the planet should be in the Alphen, like inside the Alphen surface, so that the interactions can happen. If you have a very weak larger scale, I'm not talking about small scale, because the small scale will eventually fade away relatively fast, and you will be left with the dipolar and octupolar component, in the wind. Okay, so you would need a combination of a planet that is inside the surface, so it can connect with the star, So the magnetic field is not extremely small, like it's still, but at the same time, where the planet is relative to the star is also important. So, yeah. But I mean, the activity as activity level, like let's say spots or like, these things, it's not, I would say, what would affect directly. But of course, then it's more challenging to detect in activity indices, for example, because you have the rotation of the star, it's there. So you need to clean for the rotation of the star. But if you have a very low activity star on a large scale field, you would expect the planet to be outside the Alphen surface, so it cannot connect with the star.
Yes.
Thank you very much for visiting us. And
Thank
for
you.
This very pedagogical talk that allows us to follow all the points. So thank you very much for that as well. So you have been talking about potential radio signals where we can infer these SPI, also activity indicators, spectropolarimetry. And I was wondering if there is any kind of manifestation using the time series photometry, for example. Can we detect this kind of SPI also using this kind of measurements?
A lot of people work on flares, for example.
Exactly.
Yeah, absolutely.
So,
but I could not, show everything.
Yes, but we see flares, and we
Yes.
can directly relate these flares with the planets.
Yes, absolutely. There's a lot of work on that to see actually if planets that are very close to the star, they are causing additional flares. So there are work on that. And then you would compare the level of activity, for example, in dwarfs or other, to the activity rotation, basically. I don't know if you're familiar with that, and the saturation, and you would see where the stars are they behaving normally or not? Do they have more flares? There are also studies of super flares on solar-like stars that we don't have in the sun. And this was also associated to possibly a kind of magnetic interactions. But definitely, I mean, there is a lot of work done on photometry on that. I don't do it myself, but I mean, the community does it, yes.
Thank you.
Yes.
Good.
Thank you for a very nice talk. Many people up on this question.
Can you speak a bit louder so that people online can hear?
I'll try to them up. Okay, so when you think about the interaction between the planets and the star, especially, for example, for massive planets that are very close to the star, do you expect this interaction to be this sort of physical mechanism that you expect for this interaction to take place? Is it due to the modulation of the dynamo cycle and say the tidal effects, or is there some induced magnetic fields that can take place?
This is precisely actually where we have done a sample of planet host. Originally, we didn't know. No, we don't know. So we decided, okay, let's observe many stars. Well, when we started, it was like FGK stars, basically, so not M dwarfs. But I mean, this was during my PhD, so there was not a lot of small planets around M dwarfs back in the time. You can expect that the planet, because of tidal interactions, it might be generating things in the outer layer of the star. And one of the stars I didn't have time to show, Tau Bootis, it has a massive planet very close to the star. And this is a system where the star is synchronized with the planet, not the planet only with the star. So both systems are showing one side. And we detected an 8-month cycle on the star versus 22 for the sun. So we thought, well, maybe the planet through tidal interactions synchronize the outer layer, and you are adding some shear or things in the outer layer. Then in the Be Cool collaboration, where we just observe stars, cool stars, we started observing not frequently, I would say, but we started observing several F stars with shallow outer convective envelope that actually have fast cycles. So right now, we don't think it's the effect of the planet at all. But will it have an effect, the tidal specifically, on the larger scale generation dynamo? I cannot say. Could it actually enhance some parts? It's possible, but it's hard to detect them. So I don't know if I'm answering your question, but it's really hard. I think what we would need, there are models that would explain that, but as long as the observations don't answer these models, we are still at a level where, well, we still need more observations and just to be able to know if this particular mechanism can actually be at play or not.
No, yes, thank you.
Thank you so much. And honestly, thank you for the invitation. Thank you for the invitation. It's an amazing place, so I'm really happy to be here.
So he will be here also tomorrow, or okay. So just feel free to contact Pedro or Cristina if you want to discuss with her. Okay.
Thank you so much. Oh yes, so I thank you so much.